Don't give away the whole
Yeah,
thing.
I'm gonna be going through the whole thing.
All right.
Yeah, so thanks for having me, it's a pleasure to be here and, just be warned, I'm not a public speaker in any way, but I figured it's worth sharing, my path so far so that maybe you can get some perspective and hopefully you'll have some questions and then, we can have a discussion. But I just want to share because I kind of wish I had some of this insight when I was going through school, right? So. All right. Next, go to next. I guess I'll have to click the circle. So anyways, yeah, we'll go through my, quick introduction, talk about education and then my early career and then mid-career. And, I have worked at quite a few places, but, the longest place was 12 years at Raymond down in Greene, New York, which is not too far from here, south. So I graduated, from Harborsville Central High School. And originally I was thinking about civil engineering is what, my path was gonna be civil engineering because back then I think there was a pipeline that was getting put in the area. So kind of somebody said, hey, why don't you do civil engineering? So I was thinking, sure, I'll go that path. I liked physics and I was gonna come here to Oneonta, then go and transfer to do civil engineering. However, when I took electronic circuits with Dr. French here, it kind of just, right there, I found my spark, that's what I had there, because it just made sense. So I can visualize and understand basically electronics pretty well, and that's what served me so far through my career. So I've usually been able to progress and keep working on interesting things that keep me driven, I guess, basically. Let's see. And so originally I was thinking computer engineering because I like computers. However, just so you know, computer engineering sometimes focuses a lot on software, and that's operating systems and things like that, which is important, don't get me wrong, but I like the hardware part, like some of the VHDL or the ASICs and things like that make a computer work. So that's when I did transfer to Binghamton University as a computer engineering, but I switched to electrical engineering. I just said that, okay. So one thing, is a takeaway is try to get some experience, work experience, whether it be a hobby in the field that it interests you. So it's whatever interests you, you'll have a passion in. It's going to make it a lot easier to work on and it'll be enjoyable. You just build up that experience so that it's going to make it easier to get your first, job and start your career basically. So early on, while I was at Binghamton University, I lucked out and I did get an internship at Universal Instruments. And while I worked there, I worked in a test lab and I was basically working on, they had circuit cards that did like control electronics for moving the gantries, X, Y, for pick and place machines. Basically build circuit cards to put the little chips on the boards. And in the test lab, we had to functionally test these circuit cards to make sure they were functional so that when they assemble it, it's good when they go to put it in the final assembly. So I got to work on harnessing some software and, a lot of the test equipment, oscilloscopes and what have you. And that helped give me a lot of experience. And I guess I did a good enough job and they wanted me on as part-time. So my last year of school, I was working part-time, which is a nice gig because, one, it pays better, and two, it's interesting work than going and working at, say, Sears or Arby's or things like I did earlier. Yeah, learning how to read data sheets and per component stuff. That's stuff that, like, I think some places you start to get that when you get into engineering schools, but even at Binghamton University, I don't think they were hands-on where you're really learning how to read component data sheets that you're going to be integrating on a circuit card. So those are things I learned there. There was so another interesting kind of path, why I bring it up here, is my senior project. I worked at Binghamton University. I worked with it was BAE Systems at the time, and it was the placement of bypass capacitors on high-speed digital design. So, every mobile device you have or any circuits these days, has a processor, microcontroller, and on there it has these little capacitors, and it's basically energy storage. And we had to study, how to. You basically wanted to see how can we reduce the amount of those capacitors we need to put on a board. So that was our senior project, and we were almost building a simulation in MATLAB. So instead of they have simulation tools out there, but they just wanted us to study this and do it in MATLAB. For some reason, we did have 3 mechanical engineers on that project, so a lot of that was just the computational aspect of it and understanding dimensions, but it was mostly electrical, and that's where really I took that senior project, and it kind of set my path forward as I moved on in industry, and I focused on high-speed digital design. So any single board computers or any computer hardware, anything that's doing compute, that's what I primarily focus on. That's what I'd say I'm a subject matter expert in. That's what they call these things, the SME, because everybody likes TLA's 3-letter acronyms. So there's some humor there. So then, I do have a book recommendation here, and that's where I was during doing the senior project. The mentor we had at BAE Systems, Charles Moy, which he showed us this book, High Speed Digital Design, a Handbook of Black Magic. So I put that in here, and I think you get like these slides or something, and you'll be able to go here if you want. But it's a very good book. It's good recipes. What did I throw in here too? Oh, I put that on the wrong slide. So anyways, I'll talk about it now. So with these pick and place machines, I'll come back to it. That was, if you didn't, that was like a nozzle that the pick and place machine. So I said, so one thing about, when you're working, I'm electrical engineer out of school, right? But having a strong foundation in physics is very useful, no matter whether it's software, electrical, or mechanical. Everything, right, has the basis really in physics when you look at it. It also helps you understand and perceive, these other disciplines. And if you can work with them, it makes collaboration a lot easier. Because everything takes teamwork, really. So like I mentioned about the pick and place machines, I have circuit boards that, we'll show at the end here. But I got this video, hopefully it'll work. I don't really care about the sound, so. Let me pause it. Let's see. I didn't think about that ahead of time. Let me share the whole screen. So this here is basically a pick and place machine. This is called the lightning head at the time. And so what it's doing here is it's picking up these little tiny chips, for resistors or capacitors, and it's using vacuum venturi really to suck up the part, hold it on there on the nozzle, and then it's placing it on this circuit board really fast and precise is the other reason. But I wanted to kind of show this because I worked on this control circuit up on the lightning head, and then there's this little sensor right here. That's what they call the vertical part sensor. So what happens if you get this little tiny 0402 resistor or whatever smaller, you can suck it up on its side. So then it's like it won't get placed properly. So if we can detect that before we put it on a board, we're not going to put bad boards out when it comes at the end of the line. So they want to be able to detect that. So yeah, that's what the images were on the previous page. So I'll show you that. But that was like one of the biggest projects I worked on when I first started at Universal. And the reason I got to work on it is because attrition. So people were leaving Universal Instruments. And then I was able, when you're first out of school, you don't really pay attention to the politics and everything else that's happening at business. You just want to learn and solve problems. And that's what I was doing. So I got to work on this project, which is really a senior level project while I was. I want to watch this. Let's go back. And then it stopped. So right here, those images right here. That's basically the parts. So this is like a little 0402 resistor or whatever. You can see how it gets corner stuck basically. And when you go to place it on the pads, it's not going to adhere to where the solder paste is. There's solder paste there, which is a whole other topic. But there's solder paste that holds it in place before it goes through a reflow, and then which then it's solidified and it's held there. So, yep. And through all those things, right, there's a lot of physics involved. So I also wrote the VHDL code that was reading this image out from a CMOS sensor. And I wrote, so while I was reading out line by line, there was an algorithm that would find the bottom of the part. So basically, we know how thick this part was going to be, right? So then when I take and, show the bottom of the part and it's thicker than the nozzle that we know where it's going to be a fixed location every time, they know that it's, throw it away, don't put it on the board. It's that.
So that little nozzle is creating a little vacuum.
Yes.
And it's sucking the piece up into it. And it'll place the piece unless, and then your algorithm checks to see the furthest extent of it. And if it's down, it'll release the vacuum and just basically.
It puts it in like a throwaway pile.
Okay.
It's cheaper to throw these little chips away than it is to make a circuit board that's bad.
And how fast does it do this?
You saw how fast, that's really fast. I mean, it's like a 30 millisecond cycle, and there's 30 spindles on that head. So another thing that's interesting, like we talk a long time about these pick and place machines, but the one controls engineer, one time he said a statement to me, he's like, F equals MA, you can't get around that. So, because we're like that head is like 50 pounds, and they were trying to put two of those on a gantry. So then you got this big machine and it's trying to accelerate at really high rates. So it's energizing that thing. So, we would shake buildings, because these were sold. So primarily, right, the electronics are getting built over in the Far East. And so these are getting sold and put in buildings that aren't really solid concrete. So it was shaking buildings. So they had to reduce the performance to stop that. So it's very interesting.
Great, and that would be the small time part, which is the big acceleration.
Yes, exactly. Because you've seen it, it's moving really fast.
Yeah, I had a question on, so the one at the top is the correct orientation of how the resistor capacitor needs to be placed. And I know the orientation of how it goes onto the board matters. How would you be able to, is it just like it wouldn't be 90 degrees, like in the wrong direction?
So we're only looking at the height. So this is the vertical part sensor. I think what you're thinking is the theta, which is basically there's another camera that looks up.
Oh, okay.
And it does the correction.
Yeah.
So, so there is also these things called fiducials on circuit boards that orientate where the lanes are. And so it does all these corrections. So there's a lot of cameras that look down at the board, that look up at the parts so that they can get on the same coordinate system and take away all those errors.
Gotcha.
And I mean, these were down to like 20 microns of accuracy, repeatability, actually. So yeah, it was a very cool place to work. Another question? Okay, so there's that. So that was, mostly motion control PCAs. So then, they had acquisition by what I'd call ultra capitalists. Basically, they stopped new development. I started getting tasks that, didn't really align with my career goals in high-speed digital design or circuit board design. So, I definitely jumped around a bit, as you can see here. I won't go into nauseum with everything, but I did work at VA Systems as assistant engineer for a month. He didn't have me doing anything, so I was like, see ya. And then I commuted to Syracuse, and that's like an hour and a half commute. I'll talk on a later slide why that's kind of a downfall, but it was interesting work. It was, satellite systems and stuff, so totally, different environment. So you have to take into account the thermal shocks and stresses of that. Worked at Census, which they did like radar systems. So a lot of high-speed digital design I learned there. But and then I came back to Snake Creek Lasers. So like they were actually, designing the Dr. Brown. Basically, he was making solid state green lasers. And I had to work on that a little bit and actually try to make a control to control the amount of power coming out of this solid state laser. So we had a photodiode for feedback. However, this solid state laser, which I believe used some, can't remember the YAG crystals maybe, something like that. But anyways, the thing is not very linear when you try to control it with current. So a lot of things like if it's linear, it's easy to control. So that was an interesting job. However, basically, he did some things that didn't make sense. Like it was a government project and he was redirecting funds, which is not a good thing. So didn't really align with my values. So I'll talk about that in the future. I worked at SureScan. They do baggage scanners for airports. So your bag goes out, you check it in, it goes out through the airport, goes on all these conveyors, it's really automatic. And it gets scanned so that they can check it for any explosives or what have you. So I worked there and they actually had a fixed source X-ray scanner, which is really neat. So I got to learn a bit about X-rays. It's CCT crystals that would basically read those X-rays and the energy. It was, so I worked on a lot of circuit boards that were basically sequencing those X-rays so that basically exposing the baggage as it came through. So learned a lot. It was like 160 kilovolts DC. It was going through it like a tungsten X-ray source. And then I got to Raymond with the Raymond Corporation.
I was just thinking about the power of those X-rays. Yeah, it's pretty impressive.
There's a lot. Yeah, so when they built the high voltage source, which I think was just using diodes and capacitors to keep doubling the power up, it was all bathed in oil. And the cable was a special cable, and it was interesting. But they also had a lot of protection there, like when you're doing the test systems, like because it was a small company. I mean, there was only like 25 people there, so they let half of the people go right before I left. So that's one of the reasons why I left. But they had like the lead closets, if you will, to test these detectors in. And just like, you're showing me the Fourier transform before, like the waterfall plot. Well, they do that with the X-rays to see if that there's noise in the CCT crystals or whatever, and the X-ray beam. So there's a lot of neat stuff there that I was learning. I was helping them a little bit with research and development, where they wanted to move away from these detectors, which I think were like some peak detector. They wanted to move to an averaging of picoamps, so like a picoamp meter. But if you try to measure picoamps with op amps and stuff, you learn a lot about noise sensitivity and bias currents and things like that. So I worked on that a little bit, didn't see it all the way through, but I tried to create a prototype for test. It's the design of experiments with a physicist there. So it was really interesting. So, the work was great, but then because they kind of they're a startup company for like 8 years, and then they had some downsizing, and it was like values didn't quite align. So I was like, oh, it's time to move on. So then I worked at the Raymond Corporation, which makes forklifts. And so I worked on designing a lot of circuits there, and I was there for 12 years, so it was really good. Designed so many circuit boards that are on all the Raymond trucks. And basically modernize their process for designing them. You know, picking out the tools, as well as building a department. I was the supervisor when I left, but I kind of left because the direction, the directors didn't really, you know, have a unified vision for the future, so. So some, you know, things about continuous improvement, which is, so this is about values, basically. So, Kaizen, yeah, exactly. And which is a big thing at Raymond, you know, because they are owned by Toyota, so they're always about Kaizens, which are small improvements, because if you make a lot of small improvements, you're gonna make a big improvement over time. So I'm always looking for continuous improvement, so that's one of my, you know, core values, if you will. But when I was at, when I went to Sneaker Glazers, the one thing that Dr. Brown said is like, because I was like leaving this one place because I wanted stability. He's like, well, you know, just where you work isn't stability. He told me, he's like, knowledge is stability. That's why basically no company is going to give you stability. If you keep working on yourself and your knowledge and keeping your interest in moving ahead, then you'll have stability. Because pretty much anywhere I wanted to go, I had the option to go. I had other job opportunities to go south, but my roots were here in upstate, so it didn't happen, which is fine because I'm pretty happy where I am today. Another colleague I worked with, he always had the saying, can't know it, which I like, because you can't know everything. You just can't. So you're going to work with others, you're going to research it, you're going to learn it. Because there's one thing, you know, you can't know it, but a pet peeve of mine is I don't believe in can't do, because there's always a way to figure it out. And, you know, one thing, you know, takeaway I tell you guys is basically, you know, work on some of that self-reflection, you know, early on, so that you can maybe understand what your core values are and what guides you. You know, here's some of the ones that I have, which is, you know, collaboration, helping others, creative problem solving, initiative. Basically, if I see a problem or I see somebody having an issue, I'm going to lend a hand and help out. Perseverance and tenacity, so grit. Intuition. So I do like to intuitively learn a lot of things. Like when I was working on my master's, I was telling Dr. French earlier, I just finished that in 21. So I worked on it one class at a time while I was working at Raymond. They paid for it, which was nice. But every time I was taking a class, something at work, some problem at work was you know, coming up about the same time I was taking the class, like cybersecurity. I took a class on that. I took a class on detection theory, which is a lot of statistics and everything about the ideal detectors. Like a moving average isn't, there's an actual mathematical way to find out if the moving average is the best detector to use for hypothesis testing, you know, things like that. So a lot of things that you may just take for granted. It was an interesting class. I didn't necessarily apply it to that level, but the intuition I took from it. And then adventure. So like going on hikes or whatever. So that's something that I do, kayaking and everything. See you, Dr. French. Thanks. See you. So at Raymond, this is basically one of the biggest projects I work on. This is the iWarehouse display, telematics unit, if you will. And it collects a bunch of data, just like your cars today, right? It has this infotainment system in the middle, which has everything. Well, that's what we're doing here, but on an industrial level. So it was the first thing in the market. It's a touch screen. This is a resistive touch screen because, you know, if you're in a warehouse, people wear gloves. So back then, not every glove had the e-touch, which they do now. So this is resistive. It's running Linux. It's basically a tablet industrialized single board computer. So I designed that whole thing and helped work on the software, the Linux operating system to get it to boot. So it was quite a good project, and it was really nice to see it go through. You get a big satisfaction when you get to a project like that. Sense of purpose, if you will. Okay. So this here is basically a forklift. So this is, you know, like anything you buy online, your e-commerce is huge. So that's where Raymond is a kind of big market. With e-commerce, whether it be, it's also for food, right, distribution, everything. They use electric forklifts in these facilities, freezers. But that display lets you actually see a video up here. There's a video camera that lets you make sure that you're not going to go through and damage the products. You have, like, say, a big screen TV up there, you don't want to put the forks through it. And you can't really see that high, just talking like it's almost 40 feet in the air. And so that was a nice project that I worked on. Right there's a display. That's the only snippet I could find of it. But that was, there's so many things with the forklifts that you don't think about, and it was definitely, it was a great place to work and a lot to learn. This camera actually also was a high dynamic range camera, which basically gives you like 120 dB of, optical, be able to see basically in the dark almost, because it can pull out all that signal from the photons. So again, it's good to have intuition and a basis in physics to understand some of those things. Let's see what I had next. Here's the actual circuit card that's in there. This was a 14-layer circuit board. That's the main processor in the middle, with a lot of high-speed interfaces coming out of it. So like your DDR, this has a DDR3, and you have to do matched lengths, electrical lengths, in order to make it work for all the timing and what have you. So this is Altium Designer. It's a nice tool that lets you achieve tasks. Any questions so far?
So a 14-layer circuit board?
Up 14 layers. Yeah, I actually have it here, so I'll, we'll take it, pass this around if you want. The main process is that silver thing right there. Yeah, that has a lot of nets too. So there's a lot going on with this thing. So it's USB 3.0, and I did this back in like 2015, and they're still using it today.
You mentioned that this program was Altium, right?
Yes, this is Altium.
How many, like, through your different jobs that you've been through, how many companies were using that program? If you were.
I think this is the only one.
Oh, really?
So
Okay.
when I originally started, it was OrCAD.
Gotcha.
Is what they use, OrCAD or Cadence. And then when I was at Census, they used PCAD, I think, for pads. And now where I'm working at BA Systems, they're using Expedition.
All right.
So there's a lot of different tools out there, but
Yeah.
it's really a good idea to understand the concept and the flow behind them,
Mhm.
so that you can easily move.
Yeah, here, I know when I was taking circuits, they were using Eagle, but
Eagle's good.
I think that software is going offline in like 2025,
So-
so if you're doing Fusion 360.
I would suggest KeyCAD. I don't know if you've seen KeyCAD,
Okay,
but that's an open source tool.
gotcha.
Gives you all that functionality without having to worry about paying for it.
Okay.
I think Eagle was acquired by AutoCAD, and that's
Yeah.
probably why it's going away.
Yeah.
But KeyCAD's a really good tool. I use that for some home stuff.
All right.
But I like this tool, and I used it for 12 years, so I'm biased. And I help drive the department and always use the tool better. Like every year I would kind of do Kaizens and try to use the tool better, right? To automate things and make it so that we didn't make as many errors. Because as you see here, there's a lot going on. So if you make design rules, that really helps reduce errors, because going through, say, I don't know, 5,000-6,000 nets and looking at every net length is not easy. But if you make a rule that says, all these things have to be within this range, well, it's a lot easier. And then the tool can also, you just drag it and it'll automatically add those squiggles. So use the tools, be more efficient. But you do have to know about it. Oh, this is that SureScan. Getting close. So this is the SureScan scanner. So these are those X-ray sources that were layered. Basically, there's 3 different planes so that they can look through it. And one of the benefits of this is they could tell the difference. They get the atomic number of the material. So they can tell the difference between peanut butter and C4. That was a big thing. Whereas a lot of the scanners that they use today, or when this was being developed, was, you know, CT scanners like you have at hospitals. So they have a moving source, where this is fixed, so you don't have that mechanical wear.
What's the size of that? Is that?
It's big. I mean, the opening is like
Yeah,
that
okay.
big. So it's like, it's pretty huge. It's supposed to be able to sense 1,000 bags an hour. So that's how fast the belt speed goes.
So with the energy that you were mentioning earlier for the X-rays, does that mean that you're doing basically nuclear shell spectroscopy then?
It might be, I don't know. That was beyond me. I was the electronics guy. Yep. So I helped, you know, there's a circuit card on here that is optical communication as you're going through, you know, optical, so that it's more immune to the noise, the electrical noise, the electric fields and such. So, and then there's also an optical signal that went from a sequencer, which I designed, which would actually fire them at a certain time. So
You can get some content scattering and stuff like that, I think. Actually.
I think so. I mean,
That was provide the electrons for the noise.
yeah,
So,
yeah. And yeah, they were doing some really cool stuff when they were taking the data. And but yeah, I didn't focus on that portion of it.
Yeah.
Yeah, but I thought it was super interesting. And let's see what else I got here next. Oh, and then this is kind of a blast from the past. This was the first year that we, you know, the physics club, we went into the pumpkin chunking competition with Dr. French. This is the first year we went. That's like 100-pound or a 30-pound pumpkin up here, and we'd shoot it really far. So the first year we went, because the way you got scored is it was not just distance. Like a lot of times they use the game trees or whatever it was, trebuchets. That's what they use most of the time.
Yep.
So we did the slingshot, and so that we could, you know, basically have weight times distance. So that's how we won. The second year we got second place. I'll talk about one of these other pictures. But yeah, Dr. French rented that moving truck so we can go to Dutchess County, basically. There's another view of it. That's Will Knorr.
French's house.
Yep, exactly. Yep. There's a side profile. So, I mean, it was pretty cool. You know, it just kind of just came out of intuition. We just built it, made it happen.
So what angle is that launching at?
I can't recall. I know it was somewhat important.
Because it looks like it's at like 60 degrees something.
I think so. Just feel like that. I don't even think we took and optimized it. We kind of just, once you get in the build mode, we built it. And then we kind of went that way. And we just, you know, we had these big, basically surgical pants, and it's a lot. This is like a two ton come along. And so we're actually like breaking those. So we had to go through and get like a 3-ton version because we broke one. And then we'd cut a link of chain to launch it. It was pretty phenomenal. It was awesome. So this is the first year, we won. Or no, this wasn't the first year. This is the second year where we didn't win. And
Chung Wong to the right?
yes, that's Chung Wong. Yep. Yeah, that's me up in the top left a long time ago. But this year we didn't win. So we had it on a trailer. So instead of renting the moving truck like the year before, you know, this fella here, I can't remember his name, but he actually, you know, he was going to drive it there for us with a trailer. So we put it on a trailer so we didn't have to disassemble it and assemble it. However, we didn't think it through that much. But when we had this impulse of energy, what do you think is going to happen? We're sending like really fast. We're sending this, you know, 30-pound pumpkin. We're trying to launch it. We're going to have a equal and opposite reaction there. Basically moved the whole truck. So we lost feet. So we lost that competition. And that was what I had. So yeah, so now, you know, I tried my best to kind of go through a thread of my career. It's been kind of driven on values and trying to stay ahead and work on interesting stuff that is meaningful work, basically. Because obviously you got to work to make money, but it's also nice to enjoy it.
It sounds like you like a variety of work.
Oh yeah, anything that's has an interesting problem to solve. It's nice. I do not like the mundane, and I'm not a paper pusher, so I'm not good at that. I like to be on the development side, which I have been fortunate enough to do, solving those problems, designing something. Even troubleshooting. So right now at work, I am troubleshooting something. It's a computer that was built in like 1979. And it's all like individual ALUs, like stuff that's in a microcontroller that's like this big. It's like this big. It's all individual gates. And so I'm trying to help find a problem because it stopped working. So that's been my task for the last like 3 weeks. So I'm learning stuff that kind of like was used in like space, you know, stuff.
So
Old computers.
So they don't want to replace this?
No, that was not, no, because like, you know, like in aerospace, which I'm learning, you know, I've been there for 6 months. If it's not broke, they don't want to fix it. Because there is so much effort on qualification of everything that goes in airplanes, which is, I think we all like that. And so it's tested to the nth degree, so they don't want to really, they don't just, it's really expensive, so they don't just refresh them.
I think the certification is ASI 3001 for machine parts. I'm not sure what how the circuits, I took a machine shop class in high school.
Yeah. But I think like some of the process is driven by 9145, AS 9145. But yeah, it's interesting stuff. So that's what I'm kind of learning now. And usually a lot of times like computers that are used in aerospace, like instead of just having this one computer, there'd be 3 of them. And then they're talking to each other so that if one fails, one could take over. So it's called triplets.
Yes.
Fail safe, yeah. Exactly. So yeah, is there any questions? Yeah.
The early career search, what sort of things do these companies look for in transfer?
So, I mean, if there's any, like, so if you're getting a full-time job, it's nice to have some level of experience. So that's like either you're doing it through your hobby, or maybe you got like a co-op or an internship. So that's something that's usually looked at. And of course, they also, you know, look for what major you're in, but that's an obvious. But having some level of experience is good. So, you know, I was able to get a co-op, which was nice because Binghamton University doesn't force one. And a lot of the state schools don't have an official co-op program. But I definitely recommend trying to get an internship somewhere, anywhere, and get some of that real life experience. Because you're going to be able to learn some of like the culture, the whole office thing. Some people don't like, but you know, it's good to learn those things, you know, how to navigate it. The big thing is trying to see what you're most interested in, because it's very broad, the field, you know, so that answers it correctly.
If somebody wanted to get into what you do specifically, like microchip related stuff, you said it's good to have like a hobby as like a form of experience. What would you recommend as like a hobby to better understand the work?
Well, I know one thing that, you know, Dr. Gallagher brought up earlier was there was an experiment that using like some sensor, it was ultrasonic sensor. And right?
Yes, there is.
Yeah, so that is an interesting problem right there that has some, obviously some C code or some microcontroller code. It's got a system because you're driving the sensor and you're getting some analog readings out of it. You have to interpret that. So that kind of system and putting it together and being able to explain it to somebody who's looking to hire you is very powerful. So basically having those types of things is good. You know, I was kind of into radio control stuff when I was younger. So that kind of helped pique my interest in that. However, I didn't necessarily make any custom electronics then. And then really I didn't do that until I got my test engineering job.
You mentioned doing your own circuit board work as like your own hobby type stuff. Do you make your own circuit boards by any chance, or do you normally send them out to like a board house?
Yeah, I don't make them. I don't etch my own boards.
Okay.
I did it once in high school. We like did a 2-layer board and etched it, but no, I would send it out.
Okay.
Like batch PCB or JL PCB. So there's a bunch of sources that you can get in 4 weeks. You can get a low cost circuit board.
Oh, nice. Okay.
So to do that, what do you have to, you just.
No,
Mind
Andrew
your
said,
manners.
Andrew said, oh God, the second you. So the second you paused, I'm sorry.
Uh, So he has a design for the board we're looking at. What we struggle with is soldering it. Because.
Small parts, yeah.
Small parts, and, so we wind up applying a lot of potential to the board, sometimes. So if we were to send them out, you send the design for the board and the parts that you'd want on it, or?
Well, that's if you want a full turnkey is what they call it, full turnkey board. There is places that do that, but it costs a lot more, right?
Okay.
But if you could pick parts that are larger so that you can solder them yourself under like a microscope, it's a lot better. Like use OE05 or bigger resistors and caps, you know, and then don't use any BGAs or any really non-leaded parts, you know, for building it. And then you can build it by hand. Yeah, this one still has small parts. But usually you use bigger parts to be able to do it. Like, you know, one place that's like interesting, I go every day is hackaday.com. It's a good resource that shows people that are basically have hobbies and making stuff or breaking stuff and electronics. So that's a good source. Hackaday.com. Yeah, that's a plug, yeah, sure. Then there's /.org. That's the other one I go to a lot. It's kind of geek news or whatever you call it. Yeah.
I'm sorry, you may have mentioned this before, but the programs that you're writing that you were writing for the Raymond Corporation, what software were you using to like write that
A
code?
whole bunch of software. So a lot of times it's C code.
Okay.
A lot of times you see. But then there was like when you're in the Linux operating system, so that's an operating system, it has shell scripts and things like that. So it's actually running a full file system and an OS on it, just like your Android phone is Linux. I guess even Apple's a Linux operating system at the base and has a file system. So you do have to understand that, like for that level of board.
Okay.
But for all like the microcontroller stuff, that's just C.
Okay.
And you're gonna use compilers from whatever manufacturer makes that microcontroller, whether it be Texas Instruments, Microchip, or NXP. Yeah, there's so many of them. And a lot of times now the tools are free, which is nice. Back in the day when I first started, you had to buy like the compilers. Now you don't have to. They're just given because they're usually open source. They're all built from the same IDE, which is Eclipse, and then they put a different front end on it. That's part of the can't know it. You just go figure it out. That's kind of what I always try to do.
How often do you use Google?
All the time. All the time. I mean, sometimes people don't like Google because they feel they're evil because they are collecting a lot of data from you, which I agree. So, like, if it's something that's like different, like DuckDuckGo is somewhat okay, but Google is the best. It's just they have so much data. They're able to be contextualized. So, and then you use. So, I swear there needs to be a class in Googling because
Especially now.
when you're trying to search for stuff, you need to get clues of what words to use and then change it up. And then you're going to find more relevant information. You'll solve your problem or learn it.
It's machine learning reversed.
Pretty much, yeah. I am a machine. I'm trying to learn it.
Yeah.
Yep.
So did you say that you went to grad school in 21?
I graduated in 21,
Oh,
so
okay.
it took me 4 years. Like 2016, I started that.
So would you recommend just waiting until you find somebody who would pay for it?
A lot of places will pay for it. Almost any place I've been, they have a program to pay for it. Now sometimes it comes with stipulations, says, if we're gonna get your master's, well, you have to stay here for so much time. Like Raymond was pretty lenient. I think it was only like 6 months or something. It wasn't very long. Whereas at BAE Systems, I think they're more like a year or two, else you have to pay back part of it. Which makes sense, because I mean, it is a big investment for them. I mean, I think it was probably gonna be roughly $30,000 they invested. But it's nice because, and the reason that companies do it is because it helps them, right? Because you are investing in yourself and learning more, becoming more valuable to them from a technical perspective, but it's also valuable to you because now you have more knowledge, more stability. So you can go anywhere once you take care of whatever time you had to be there. But usually you're going to do that because it's a place that you enjoy working at the moment. So hopefully it
So-
stays that way.
You said it took you 4 years. Is it like, do you take your time there?
I took my time. I did one class at a time because I didn't tell you this part of the story, because when I first got out, Universal was paying for masters too. So right out getting out of school and get a full-time job, I'm gonna start taking my masters. So I started working on that because they like to see masters, because then they have some pie chart that says, we have so many people that have masters, right? So many people with PhDs. So they're promoting it. So I took and started there, but then my son was born. It's like one of my core values is family, right? Which is time. You don't get time back. So I didn't have time to take it, so I just stopped. I took one class and I was done. And then I started back up sometime later. And they reminded me, like, we can't count that one class. I was like, I didn't expect you to. So I went to the same place. But yeah, I took my time. And then you get, instead of rushing through the material, I got to focus on each subject. And they did have like engineering project at the end, rather than like a thesis. So I did a project, and it was designing of a high efficiency DC to DC switching regulator, digital one, using the DSP, GaN FETs and stuff. So a lot of analysis did for that. Lost that train of thought. Happens, right?
Yeah, all the time. Especially, like now. If you could apply the self-reflection to yourself when you were here, what do you think you would have done differently?
Probably would have got more involved in what I thought my future career was going to be, and I actually did more of the building the circuit boards or doing these like projects. Because I think, I didn't do as much of that then.
You did conduct research with Dr.
Yes,
Lever,
yep, the vibrating sample magnometer, worked on that, that was fun.
and with Dr. French.
Yep.
Other questions?
Books you read on to today. You can just teach yourself material based on what you read.
I mean, like the one electronics book, the high-speed digital design. I read that. So that was I wasn't a big reader, like reading novels or anything. But that book I read cover to cover right when I graduated my degree. When I got a full-time job at Universal Instruments, I read that cover to cover, and basically became their signal integrity guru because they didn't have one. Like they would run a high-speed trace that was 100 megahertz and had a rise time of say 1 nanosecond or something, which is a gigahertz, pretty high speed. And the thing with these high speeds is for every edge, right, that's a lot of current, instantaneous current that you need. It travels in loops. So I read that book cover to cover, and I typically will go and read almost any data sheet and try to read and understand it and be able to comprehend it and keep going at it until I can figure it out. At least enough to where I'm going to solve some problem. Like with this problem I'm working on right now with this old computer, which is like, there's no C code, there's no assembly code. It's actually microcode that they designed in themselves. It's using proms and some sequencer that's going through and doing the CPU. It's like CPU this big. So that I'm learning and looking at really old documentation and reading their data sheets. And some of it's pretty good, but it's hard. But keep at it. Away.
I'm surprised they haven't stuff. You know, it's from the seventies.
They're still manufacturing, they're building planes this day, brand new planes like the freighters that, like FedEx and stuff use. They're still putting this in there. It's pretty cool.
So, and they still haven't documented it in a more modern format.
Yeah, they have pretty good documentation though, luckily, even though the fact that, like their facility was flooded, so they lost a lot of stuff, but they actually have quite a bit of documentation still, so it was saved. Because that whole facility in Johnson City in 2011 was flooded, so then they relocated to the IBM campus. So IBM is from Endicott. There's actually like, you can have a whole nother topic about a lot of the industry that started in upstate New York. Utica was known for a lot of like radar, as well as Syracuse radar systems, a lot of cutting edge stuff that was done.
Because you showed still a lot of radar being done up there.
Yep, which is, I worked at Census, which does that, yeah. And then,
Griffiths Laboratory, which is
at the Rome,
the Air Force, Air Force Laboratory, Corning.
yep. Yeah, and then, in Endicott, right, IBM, that's huge. And then eventually it left, but there's a lot of industry and technology, and then up in Kodak and Rochester, which we actually visited there with the physics club with Sonella Brew, back when I was here, which was nice.
I still have that picture somewhere. There's a picture of you guys taken up there.
Yeah. The only downside though, to be honest, was they were handing out pink slips on that day. So there wasn't as many like people there, but obviously the ones that were safe were still there showing us around. Showing us the inkjet printers, the CMOS sensors and CCD sensors and lots of cool things.
You guys came back talking about the inkjet.
Yep.
And I remember in electricity and magnetism, a problem. It was actually in a textbook written by a guy from Cornell, but it looked at establishing drop size. Basically the balance of electrostatic energy and surface tension energy. And the drops break apart to minimize the energy. And you can design the size of the drop using the electrostatic control. So these guys were doing it the other day.
Oh.
Never mind. When you were doing the electrostatic energy project.
Oh.
Yep. When you went to Bennington, are there some hands-on skills that you wish you had down there that you didn't get from here? It's a long time ago.
I have a visual memory though, which is nice. That helps me out. No, I felt prepared when I went there actually. We started using oscilloscopes and things like that. And then, luckily I think we did a little bit of MATLAB here right before I left. So that was nice because they used it a lot there for signals and systems.
I think, so did you take computational
I
physics?
did. I took it with Dr. French.
Okay.
We used BASIC then.
Right, no.
And I was the only person who took the class because we had 3 people sign up and then the other 2 dropped out.
Okay.
But it was a good class.
I think the next time it was offered, I taught it, and we switched to MATLAB.
Yep.
So that people could prepare.
Yep.
Dr. Nolenberg still does that.
Yeah, that's good. It's a tool and it's used actually in industry too, like for control systems and what have you.
He's waiting for me to die so he can switch to Python, but other than that, it's,
I mean, Python's nice because, right, you don't need MATLAB, but
Well, MATLAB is also nice because you can easily go to Python or Fortran or C.
they're all similar. I mean, to be honest, you got Perl, Python, whatever code, whatever it is, you just need to understand the structure and how to solve the problem. And get over those limitations and be able to Google syntax and move on. That's it. But like there's Octave, I think is an open source version of MATLAB, so, and then Scilab or something. is another one.
Yeah, I've heard of that.
Yeah. So I usually look for open source stuff. I like that. Yeah.
You guys are nuts.
Yeah.
Then you don't, it's hard, well, the thing is to work so hard to know what's in it.
Yeah.
You know,
A little bit.
With one trend,
I
everything.
think when
is
you learn,
fixed.
when you learn it.
no, it's true, when you learn to, like, you know, you can use a canned FFT to do signal processing. But if you have students write their own, then whatever environment they switch to, they can write a quick test code and verify whatever's there.
Well, it's imperative that you do learn what's going on behind the scenes. Don't just use the canned tools. Because it's, yeah, there's different ways that they do the numerical analysis than what you learn in the textbook. So it's important to do it by the long way first, before you just take for granted the tools that are out there. But there was like a tool that I came across, was finite element magnetic modeling. It's an open source tool. So I use that because on one of the forklifts, there's like a tiller arm. And we were thinking about putting magnets on the end of it and then being able to sense those that magnetic field on a sensor, just know what angle we were at. So, you know, I used the tool like that to see what field strength we were gonna have and stuff like that. So it's like, when there's a problem, you go find the tool to help solve it. And that's one thing I did. And IT never liked it because I was installing so many random tools, but
He was gonna ask a question and then you just piqued his interest with the finite element.
Yeah, it was actually directed towards you. What's a can? FFT.
Canned,
So
Yeah.
something that's just pre-made.
it's pre-made.
they were pre-made, they
It's
optimized
in
it.
there and you don't know what's in it, but it's, you don't know how it does what it does,
And maybe,
you just believe it.
maybe they're using an approximation, or maybe they're using a certain window function that's going to give you the results that you apply to your own data.
So when we read that signal processing paper, you coded your own DFT, which was slower, but we needed something fast.
Yeah.
And MATLAB has an FFT that you just say FFT blank and it's good for that.
Yeah, I know, I use that in computation during my class.
It's a little weird because it does real and complex parts and it starts in the middle of the array and works out to the edges, which I don't get. But takes a while to figure that out.
It gets even weirder when you start using the CUDA cores or whatever for NVIDIA to help speed it up through parallel processing.
All right.
So other questions?
I have some other circuit boards.
Sorry.
Go ahead.
I won't take too much of your time.
No, it's fine, that's why I'm here.
When you're working in this, the people you work with, what's it for sort of the background?
Their degrees?
What was it like diversity? What was it just in physics at all?
I did work with Andreas, he's just physics major only.
He was just a
Oh.
physics major.
And then I worked with a person at SureScan, he was a physicist. So, and I think he got his physics degree in audio, though, sonic or something, Eric Johnson. So yeah, I worked with those folks, a lot of them, but then there is like usually a lot of engineers, you know, mechanical, software, computer engineers. Usually computer engineer is a blend between software and hardware. Yeah, pretty much all those folks. There was actually, one of the software engineers was he got his mathematics degree, so some people get their regular degrees and go get a job in the industry.
So I just a question on the difference between electrical software and then controls engineering. Because I know like they work together, but I know they all do stuff different, right?
You mean computer engineer or controls engineer?
Controls.
So controls is typically like, that's gonna be the mathematical, basically controlling of some thing, like say speed in a motor.
Okay.
And you're gonna basically look for the feedback paths and understand what the gains need to be to control that and keep it stable. So when you put a step response in, is it gonna oscillate or is it gonna get up to speed? You know, is it gonna get there in a certain amount of time, basically? So that's like controls engineering. And then airplanes that, I haven't really done it, but it's to control the surfaces. So they're gonna use feedback from the pitch and yaw and everything sensors in order to control those surfaces to keep the plane stable, because without the electronics in some of these modern planes, they wouldn't fly. They're just human, not like the Wright brothers can just control the flaps. They have to all work in conjunction. So, and they get pretty big different loops, like in just positioning a motor, position loops, velocity loops, and like current loops, all those types of things. And they have to close in a certain amount of time and understand the stability. That's like controls engineering. And you do take a control circuit class when you do electrical engineering. It's an option. Like I took 1 and 2. It was interesting.
And that is a lot of work with, stepper motors and, what's the other thing? It's common.
Brushless DC. But there's, just the brush motors too,
Yeah,
which is just a voltage, basically controlling the voltage to it. It's going to control the speed. Or stepper motor, you're doing micro steps.
right.
So on the forklifts that you showed earlier, 40 feet is quite a torque arm for for a metric ton, right? So are there, so those are meant to be used indoors outside of wind?
Correct. It's indoors only, and it's nice. And they have a specification for the concrete floors. And then you have to get trained to operate. So when you're up there, right, it's a big old cantilever. And the thing is, though, there's load wheels that are out in front of you.
Okay.
So there's load wheels like right there. So you're lifting straight up. But there is a moment in time when it reaches into the rack and it lifts it up to where you're holding it there, and you have counterweight behind you because there's a battery. And they use lead acid batteries. And one nice thing about the lead acid battery is the counterweight.
Exactly.
So that's one reason they use it. So then they're starting to use lithium ion. But to use lithium ion, they have to put a bunch of steel in there to make a counterweight. Because it's really important for that problem.
Why would they switch to lithium ion?
Because it's more efficient.
Yeah.
With the lead acid batteries, there's more source resistance in the battery, and they deteriorate over time. So you get a lot of losses from that. And then a lot of times when you're doing like a lift operation, you're spinning up the motor, it needs a lot of current, like 1,000 amps really fast. So with lithium ion, you can give that power faster. So therefore you're gonna get less I squared R loss and stuff like that. And they're trying to go to higher voltages, but they haven't done that yet.
Yeah.
They're running at 24, 36, and 48 volts. But the problem is you go higher than your shock risk. So I think like 48 volts above is like I think 52 volts is actually like a UL shock risk.
Did you have a question, Skylar? Oh, I thought I saw your arm pop up at something.
But I have some circuit cards if you want to come take a look before as you're leaving or whatever. And if you want any other questions.
Any other questions? All right, well, thank you guys for being here. I think the next one is in 2 weeks again. And it's Sebastian who is in, essentially, informal science education, but he had a love for astronomy here, a lot of work in the planetarium. So, and then I'm thinking, let's see. So next semester, as we look ahead, we have someone who got a PhD at Purdue and now works for one of the aerospace corporations. And then Ray Hartman, who's worked in industries locally. And then Ray Hartman's worked at Global Foundries, Regeneron, and is now at Knowles Power. Mitchell Collins, who did his 3-2, actually 4-2 at Binghamton in mechanical engineering. But he's also working at 9 Mile Point in nuclear. And then I have one more spot for next semester. Who would you like to hear from?
Nate's web.
Nate?
See how he's not laughing?
Invite Nate to come. I think Nate would, so I'm thinking of my, the the intro to engineering people who showed up. Mike gets all the stuff. You need some civil engineering perhaps, that'd be, that's what you're interested in, right? And, you're mechanical again, so we've got you taken care of. Mechanical also, right?
Slash aerospace.
Slash aerospace, so we got you hit twice. We're bringing Peter Anderson because he does some he did some app development while he was in grad school. And with Sean, you don't know what you want to do, right?
Yeah, I called him.
This is for you. All right, and the astronomers, we're working on that. Sebastian, so we got that. Yes, sir, what do you want? What's that? Oh, because we've run through a lot of them. Yeah, I mean, last year we had we had Mike from the Space Science Telescope Institute, so, and who else did we have?
We've had Kimmy recently too.
Kimmy, so.
I'll come to the civil
Okay. Okay, so I have, so it looks like civil engineer, I have to find a civil engineer. Go ahead, I have two in mind.
Why not just an oddball, like somebody that's doing something,
Like a wackadoodle?
kinda, yes, like that, and maybe it'll spark something.
You can present.
What? I have, I do have a talk ready. I was gonna do one of the first one, yeah. No, that's a fair point. All right, so civil engineer and a wackadoo. And more astronomy. We did have someone else come, go ahead. What's that? So we have someone next semester, two people next semester who will be coming or working in nuclear industry. But they did no training in nuclear physics. But it is actually probably a growing field because we still have nuclear reactors, and all the people who were trained to operate them are dying to retire. Actually, they retire and they get called back.
I think they were talking about making some small reactors too. There was some new technology there.
Yeah, and there's a lot of, the US has a lot of regulation that hinders that, so. Well, for example, France has strong programs to reprocess fuel, and they're prohibited in the US. For security reasons, they don't want them to get close to weapons grade, even though they wouldn't be close to weapons grade.
Misunderstanding of how things work.
Yeah. But it is an interesting point. It's but there are lots of small reactors that are new small reactors.
Yeah, they're talking new designs that they want
Yeah.
to pursue.
Yeah. So it could be a good time for that industry.
Yep.
All right. Well, Josh, thank you very much.
Thanks for having me.
And I think we sell your